Okay, so we're going to try to do a Newman projection problem. So to do that, let's come up with a substrate. Let's try this guy. I'm going to number my carbons. I'm going to say this is 1, this is 2, 3, and 4. This is not the correct numbering that you would do if we were doing nomenclature. This is not correct. This is just arbitrary. Everybody say it with me. Completely arbitrary. Right? Completely arbitrary. Right? So I number these, and I'm going to basically say, I'm going to draw my eye. So what I like to do is draw the eye and say I want you to look down carbon C2. Right? So the problem will basically say draw a Newman projection looking down C2 to C3. So C2 will be the front, C3 will be the back. So the first thing you do is just draw a generic Newman projection. All right. Now what I didn't include in this example, I didn't include wedges and hatches, did I? So I didn't include any stereochemistry. We'll add that dimension on another problem after this. And so I didn't include stereochemistry in this one. Now all we're doing here is trying to look at the connectivity of the molecule drawn and make sure we can just translate to a Newman projection. We'll worry about the three-dimensional stuff in a second. Right? So carbon 2 is where? Carbon 2 is the one we're looking at, right? It's in the front. So the first thing you say to yourself, what is attached to carbon 2? Now remember, in organic chemistry, what do we usually not draw in? Hydrogens, right? So even though something like carbon 4 up here, look at that, can you use a laser pointer? Something like carbon 4 up here, right? There's how many hydrogens bond to that carbon? 3. How many hydrogens are bonded to carbon 2? 1, right? They're there, we just don't draw them in. But for our Newman projections, we need to draw them in. So what's attached to carbon 2? There's a CH3, so I'm just going to put that CH3 over here. What else? Another, we call this an isopropyl group. CH2, CH3, another CH3. What else is attached to carbon 2?
The third.
Carbon 2 has what else attached to it? It has a methyl, this 3-carbon unit, and what else? And a hydrogen, right? Good. Okay. So now, since we're looking down from 2 to 3, the back carbon we're looking at is carbon 3, right? So we ask ourselves, what's attached to carbon 3? So what's attached to carbon 3? So a CH3 is, and what else? An H, and then H. Yep. So we successfully drawn this Newman projection now. One way to check, right, is how many carbons are in the whole molecule in front of us. There's 1, 2, 3, 4, 5, 6, 7, right? So does our product have that many carbons? So there's 1, 2, carbon 2 and 3, 4, 5, 6, 7, 8. I numbered that wrong? One, 2, 3, 4, 5, 6, 7, huh? 1, 2, 3, 4, 5, 6, 7. Yeah, I'm glad you guys caught that. Good job. Good job, yeah. I'm glad you guys were all thinking that's what I was testing there.
How is that isopropanol from the number 2 carbon from the bottom as 2C?
This should be CH.
It doesn't make any sense. You would have like 5 bonds.
Carbon will not have 5 bonds. Let's just be CH there. Good. Okay. Okay. So now let's include a problem with stereochemistry. That means we're going to use these wedges and hatch marks. So if something's a straight line, that means it's in the plane of the paper. Wedges mean they're coming out at us, right? And these hatches mean it's going away from us, right? So what group should I put on here? Let's have fun. Okay. Let's put a bromine here. Let's put an OH here. We'll put an easy H right there. What else should we put on there? Good. O-methoxy. Good answer. O-methyl.
Oh, bismuth.
What? Bismuth. Coming on board, BI. F. Fluorine, as it were. Good. All right. So now we have this. There's 3 dimensions to this now. So when we draw this Newton projection, we have to actually include the correct spatial arrangement, right? The correct spatial arrangement, 3 dimensions. All right. So for this one, I'm going to say let's look down. Take our eyeball and let's look down this carbon from 2 to 1 to 2. It doesn't really matter. A to B. We're looking down that carbon, right? So we draw the things in the front first. So if you took carbon 1 and turned it towards you and you were looking down it, what is up here on the right? The bromine is. Good. What is down here? The H. And then what's left? The OH would be to the left there. Notice how the H was down? See how I did the Newton projection a little differently this time? Right, I did the Newton projection with the kind of the Y instead of the peace sign one. So that matters. So now if we look at, it doesn't really matter. It just makes it easier to see. Right, so for carbon 2 now, we have to ask ourselves, as the molecule is drawn, is it staggered? Is it staggered? Or is it eclipsed? So if you take a look at it, right now it's staggered. So let's draw a Newton projection to reflect that. Right, so we would draw a Newton projection that is staggered, right? So the bonds aren't on top of each other, not eclipsed. We're drawing a Newton projection that's staggered. So now we got to look at carbon 2 here and say, well, where is everything at in carbon 2? So which one of these is at the top up here on carbon 2? Ready to see that? O-methyl, right? Up here, right, is actually here. I always like to either model kits help, right? If I had the F in my right hand and the bismuth here in my left, and I turned, my right hand's still here, and bismuth is over here. So O-methyl is up top, and what did I say was here, or is going to be here? The F will be the fluorine, and the last one to fill in is the bismuth. Very good. All right. So this really matters. The 3-dimensional space arrangement really does matter a lot. Right? And we'll talk a lot about that later on, soon enough. Questions? How do we feel about this? Looking okay? Right? See it in 3 dimensions? You are going to be allowed to use your model kits, so bring your model kits, use them. Okay? So my class hasn't got to this yet, but Dr. Olmsted has, so I want to draw it, and my class will get to it eventually. Is taking a cyclohexane ring and being able to draw it in 3 dimensions. All right. So if I put this wedge bond here, right, how am I going to be able to draw the cyclohexane in 3 dimensions? Well, we do that with chair conformations. All right. Every one of these carbons, this carbon right here, 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 and here, and here, have how many hydrogens bonded to it? 2, right? 2 hydrogens bonded to it, right? And one of these hydrogens is going to be up, right, wedged, and the other one will have to be hatched, right? Right? They both can't be on the same side of the ring. Think about rings as having a top and a bottom. right? So the methyl group here is on the top of the ring. So is this hydrogen, but not this hydrogen. It's on the bottom of the ring. Okay? Now, the way we draw these things on a three-dimensional chair structure, we use these terms axial and equatorial. So based on what we've learned about geometry of these things, what's the hybridization state of all these carbons in this cyclohexane ring? They're all sp3, so what geometry do they have to take? Tetrahedral, right? So if you look at this carbon right here, right, this bond is like coming out at us, and this is going away, and these two are in the plane, right? This carbon has to have a tetrahedral geometry, so we have to show that representing in 3 dimensions. This bond will have a H, right? And this H is on the top of the ring, right? It's like this, it's this H. It's on the top of the ring. The other H on the bottom of the ring, right, is there. This is the H on the bottom of the ring. Everybody see how they're on different sides of the ring? One's pointing down, the other one's pointing up. Yes? The one pointing up, when they're in the up position, when the bond's straight like this, we call that axial. We call that axial. This is an axial position. Right? This position we call equatorial. Right? It's pointing out, it's more on the equator of the molecule. Now this is on the top, this is on the bottom, this is an axial position, this is an equatorial position. Okay? So what if I draw the carbon next to it? I draw a bond going down and a bond going up. Right? Because this carbon right here is also tetrahedral, right? It also has an H in both positions. So if I number these carbons as 1, 2, and 3, this is carbon 2, this is carbon 3, right? So one of the H's in 3 is going up and one's going back.
I get it.
Alright, so let's see. If I labeled these, I'm going to try to actually... hold on, let me do it. Okay. But now, what position is this H in? Axial or equatorial?
Axial.
It's axial. But is it on the bottom of the ring or the top of the ring? It's on the bottom of the ring. All right? It's on the bottom of the ring. This H is equatorial. And it's on the top of the ring, right? So notice, what you should notice is, on carbon 2, the axial H is on the top of the ring, and on carbon 3, the equatorial H is also on the top of the ring.
Is it so that they don't like compete?
Well, it's the most stable conformation to get things away from each other, right? Still sp3 hybridized. So what about carbon 1? Where should I put that methyl? I can put it where? Both positions would work, right? So the carbon 1, the down is kind of in 3 dimensions over here. It's harder to see. And our H is, the other H would be there. So let's draw this H and draw the CH3 in the axial position then. All right. So I'm going to circle 1 H in blue, 1 H in red. All right. 1 H in blue, 1 H in red. The CH3 is on the same side of what H? What H is it on the same side of? So the CH3 is on the top or the bottom? The bottom as I have it drawn, right? So what H is it on the same side as? The blue? Or which one's the blue on carbon 2? Is it the axial hydrogen or the equatorial hydrogen that's on the same side as the CH3? So here's my CH3. Oops. All right, there's the CH3. is a CH3 on the bottom or the top of the ring right now? Bottom. And it's in the axial position. Which H is it? Which H is the blue H here on carbon 2? Is it this H in blue or this H in blue?
The second one.
First.
The CH3 is on the bottom of the ring, right?
Right.
Which H is also on the bottom of the ring? The axial or the equatorial? The equatorial one is, right? So this is actually the blue H. You see that? Let's draw another one. What if I had let's make it harder. Alright. So we got a whole bunch of stuff on here. CH3 here. Alright. How are we going to draw this one? So the first step we need to do is what? Draw the chair. And so the easiest way to draw the chair is to draw two parallel lines. And then to draw two more parallel lines. And then again, two more. See how I did that? Parallel lines. Two more parallel lines. Kind of meeting there in the middle, but not quite touching. And then you just fill in the rest. Alright, so that draws us a chair. The other easy thing I think to do is, before we start worrying about where, where this CH3 is, where this OH is, where these guys are at, is just draw in all these types of bonds, the axial and equatorial bonds. Just start drawing them in. Alright, it's good practice. So here, this one's going up, this is going down. Axial, equatorial, axial, equatorial, axial, equatorial. Right, you notice every other one, right? On this carbon, the axial is pointing down, right? On this carbon, the axial is pointing down. On the carbon next to it, on either side, the axial is pointing up. It's on the top of the ring. Down, up, down. Down, up. Okay? Seen that? So the next thing I would do is I would just number everything in the ring. Right? 1, 2, 3, 4, 5, 6, right? And now that I have a blank canvas essentially, right? This thing is essentially a blank canvas. Right? I can arbitrarily number these 1, 2, 3, 4, 5, and 6. Alright, so let's take some time and practice. See if you guys can fill this in now. Okay, let's go ahead and try to put this on here. So, carbon 1 has an OH, and we'd say that's on the top of the ring pointing out at us or the bottom of the ring. You can say the bottom, right? It doesn't really matter. As long as your top's the top always and your bottom's the bottom always. Exactly. So let's just say the OH is on the bottom side, and we'll say the OH goes here, because this is also, we'll say, this is the bottom side of the ring down here. Okay?
So in the left, are we saying that all the wedges are up and all the...
Hatches are back.
Okay.
So the wedges are on the top ones, right? So I'll go through all the top facing bonds, right? This is an axial pointing up. This is an equatorial pointing up. Axial pointing up, equatorial pointing up. Axial pointing up, equatorial pointing up.
Okay, that makes
Right?
sense.
So we put the OH here on an equatorial pointing down because I just labeled that one carbon 1. Arbitrarily labeled it 1. So I put the OH in the equatorial position. Could I put the OH in an axial position on a different carbon? Absolutely. But I didn't. So, carbon 2 has a CH3 on it and an H. What is the relationship between OH and CH3? Are they on the same side of the ring or the opposite sides?
Opposite.
So on carbon 2 here, where should I put that? In the equatorial position or the axial position? Has to be, if it's on the opposite side of the OH is an equatorial, but it's pointing down, right? Down. The CH3 is pointing up, so they're opposite faces of the ring. So the OH and the CH3 would have to be on opposite faces. So the CH3 is going to have to be on the equatorial carbon. Right? See how this is pointing up, this is pointing down. They're different sides of the ring. Carbon 3 would just have H's on it. So I could fill in the H's, right? 2 and H. Carbon 3 has some H's on it. Carbon 6 has some H's on it. Carbon 5 has some H's on it. Carbon 4 doesn't have H's on it. Carbon 4 has a Br and a CH3. So I have two positions on carbon 4. I have this equatorial position and this axial position. So relative to this CH3 on carbon 2, the CH3 on carbon 4 is on the same side or opposite side? Same side. So what position on carbon 4 will that CH3 be? Equatorial or axial? Equatorial, right? Because this CH3 is pointing up, and the equatorial position here on carbon 4 is pointing up. So that's where we put this CH3. Now bromine just would have to be here, but if you look at it, the bromine and the OH are on the same side, and the OH you see here is pointing down. So in this case, the bromine will have to be in the axial position, pointing down as well. Could I have drawn this a completely different way? Yes. Right? I could draw it completely differently. Right? But the relative stereochemistry, right? It's always the case that this OH and this Br are on the same side. Is it always the case that OH is axial? Or is it always, is it always the case that this OH is going to be equatorial? No. It's not always the case. Right? We could do a ring flip and put this OH axial. But is this OH always going to be on the bottom side of the ring? Yes. Right.
So if you were to do a ring flip, would it just be the opposite?
So let's show a ring flip. Let me see if I can copy this. So I said we're going to practice a ring flip. Let's practice a ring flip and see what happens. So practice drawing a new chair structure. 2 parallel lines. 2 even lines, parallel. 2 more parallel lines. We're going to show what happens in a ring flip. Ugh. There it is. So the ring flipped here. So the easiest thing to do, we should first start thinking about numbering the carbons. So arbitrarily numbering the first one, I'm just going to say carbon 1, 2, 3, 4, 5, and 6. So the way a ring flip works is essentially, when we talk about a chair, I always like to think about the top here. Carbon 1 is like the head of a chair. Right? You're laying down, here's your feet, here's your footrest. What's going to happen in a ring flip is I'm going to pull the head of the chair down. I'm going to pull the leg rest up. Right? So as I pull it down, I'm pulling 1 down. So now carbon 1 is actually going to be the bottom of the leg rest. And carbon 4 got pulled up. Right? Hold on a second. Convince myself here. Okay, I'm back. I figured it out. Number your carbons. Let it be a lesson, right? So as carbon 1 gets pulled down, it becomes the footrest. Carbon 4 gets pulled up, it becomes the headrest. Yes. So here's carbon 4, and we didn't break any bonds when we did this ring flip, right? So everything's still bonded to each other. 2, 5, and 6. Okay, everybody's buying that. We can flip the ring this way. But how is this going to affect the equatorial and the axial positions on these carbons? They're also going to switch. But if something's on the top of the ring, is it always going to be on the top of the ring?
No, we.
We didn't break any bonds. If you're on the top of the ring, you're always going to be on the top of the ring. Can you be on the top of the ring in the axial position? And the equatorial there's positions in the equatorial that are up, and there's axial positions that are up. So let's see, let's just look. So we draw a blue line for the axial and a red line for the equatorial. The blue line, we'll all agree, is on the top of the ring. And the red line, we can agree, is going on the bottom of the ring. Right? So on carbon 1, the blue line was going up. What position is it going to be in carbon 1? Axial or equatorial? It was axial. After the ring flip, it's going to be equatorial, but still on the top of the ring. Right? Top of the ring, axial. Top of the ring, equatorial. So the ring flip causes something to be that was axial to now be equatorial, but it doesn't change what side of the ring it's on. Right? It didn't change the side of the ring it's on. It just changed the three-dimensional space it was in. And now the red one, right? The red bond was equatorial on the bottom of the ring, pointing down. So now it's also in the bottom ring, but now it's in the axial position. Yep. So let's look at a real example. Draw a methyl.
So you still want whatever was on top to stay on top? Just
Whatever's on top has to stay on top. Right? It just might be, if it was axial before the ring flip, it's going to be equatorial after the ring flip. Right? So let's take this example. These two things, we call this trans to each other. They're on opposite sides of the ring. The methyl and the bromine are on opposite sides of the ring. So the CH3 and the bromine are on the opposite sides of the ring. They're always going to be opposite side of the ring. So let's draw it in 3 dimensions. 2 parallel lines, 2 more parallel lines, yet 2 more parallel lines. We'll call this carbon 1 and carbon 2. We'll call this one 1 and this one 2. We'll draw in our bonds. We got axial going up, equatorial going down, axial going down, equatorial going up. Okay. Carbon 1, the CH3 is axial or equatorial? Just got to choose one. Let's just, for ease of use, let's just consider this the top. And so we'll put this as the top. We'll put CH3 right there. And then there's an H we don't include, but the H is going down as equatorial. All right, we could draw it in. Sometimes it's helpful to draw the H's in. All right? Okay. Now the BR, the CH3 and this BR are on opposite faces of the ring. So if this CH3 is axial and pointing up, where does the BR have to be? Down. So it's axial as well. They're both axial. That means there's an H right here. Good. So now what's going to happen if we do the ring flip? The CH3 will it still be on the top of the ring? Will still be up? It'll still be up, but will it be axial still? No. So we draw our other ring, 2 parallel lines. And this takes practice drawing these rings. Yep, see? Take some practice. Try it again. As soon as I said it, I'm just going to screw it up. There it is. Carbon 1 now, right? If we pull this down, the headrest down, and pull the leg rest up, carbon 1 now is down here, and carbon 2 is here. We draw in our bonds. This is axial, equatorial, axial, equatorial, right? So the CH3 was on carbon 1. It was axial before, pointing up. What position is it going to be now on carbon 1? Axial or equatorial? Has to be equatorial, right? On the top of the ring. See how this is on the top part of the ring, pointing up? That means there's an H here. So the bromine before was on the bottom part of the ring. Right? Where is it going to be on carbon 2? Axial, equatorial? It's going to be equatorial as well. And then H will be axial. Right? This is the ring flip. So you can change from axial to equatorial, but you can't change what face of the ring you're on. You can be axial and be on the top, and you can be equatorial and be on top. Now the next question of this, here's two conformations of this ring. One with the CH3 and the Br axial, and one with both of them equatorial. Which one's going to be lower in energy? Yeah, which one's going to be lower in energy and why? So you got 50-50 shot. Which one's lower in energy?
Axial.
Axial is not the right answer. So equatorial would be the right answer. And the reason why it's not axial, so this is lower in energy. Right? It stays in this conformation more of the time because of these 1,3 diaxial interactions. Right? If I start drawing in the other axial bonds, you'll start to see that when things are in the axial position, it's more likely for things to bump into each other, which of course we don't want to have happen. All right, you can see this CH3 is in a 1, 2, 3 relationship with this CH3, which is this H, which is axial, and these two things can bump into each other, right? And don't forget, our CH3 is not just a CH3, right? Those CH3 also exists in 3 dimensions. These H's are really, right, sticking out in different directions. Right? So to avoid the diaxial interactions, that's important. Right? Remember, think about how big bromine is, right? Bromine's a big old molecule. These diaxial interactions will make it less stable. So anytime you can avoid electrons getting close to each other, that's what we want to do. Good.